Good afternoon, everyone. My name is Rick Drucker, and I'm the Business Development Specialist for Lessman Instruments Industrial Hygiene and Safety Division. I'd like to thank you all for joining us for today's webinar on how to measure sub-ppm levels in a complex gas matrix. Today's industrial hygienists and EHS professionals are continually challenged with detecting and measuring sub-ppm levels of known and unknown gases, identifying unknown odors, and quantifying known compounds. Hopefully, today's webinar will help protect workers, guests, and community in and out of the workplace, including confined spaces, laboratories, etc. In today's presentation, we're going to discuss how to rapidly identify and quantify gases and vapors in real field conditions, measuring gases at sub-ppm levels, identifying the source of employee reported smells and odors and so forth, assessing chemical toxins in confined spaces, measuring multiple gases simultaneously, using Gasmet's ever-growing NIST and EPA reference library of over 5,000 gases to identify unknowns. And then, of course, at the end, we'll have Ask Your Expert so that Jim, and we also have Steve Oakes from Gasmet on the line here, can answer whatever questions that you have. We're going to ask at the end as opposed to interjecting them through. Today's speaker is Jim Cornish of Gasmet Technologies. Jim has been working in the field of environmental instrumentation for more than 25 years. He's joined Gasmet Technology all the way back in 2008 to provide applications, instrumentation, and technical support. He has extensive hands-on experience with many field analytical measurement technologies, including gas chromatography and optical measurement. He's received his BS in applied chemistry from Deakin University all the way in Australia, and is actively involved in the AIHA real-time chemical detection system courses. Little bit of housekeeping. Everybody is muted. There, as always, is the Q&A button on the bottom, as well as a chat button. So we'll be looking at all of your questions and certainly bringing them up towards the conclusion of the presentation. And with that, Jim, as always, welcome you here. We're super happy to host the seminar.
Thank you very much, Rick. Thank you for the invitation, and also thank you very much for the participants today with our topic on FTIR gas analysis. So let us start. I'm going to kind of just put myself out of view so I don't trip over any technologies issues, but let's start with getting ourselves here going. All right, so the presentation today, we're going to look at the FTIR gas analysis measurement and look very heavily orientated towards case studies and applications. A number of those have been certainly listed there that we're going to go through and how it's applied. We're going to talk very quickly on sort of the technology, definitely to discuss selectivity and sensitivity, operation briefly, some sort of publications, third-party testimony, and pricing right through to questions and answers as Rick has outlined. Often the eyes are bigger than the stomach, so I'm going to try to keep this moving. My ambition is certainly about 35-40 minutes to have this complete, and leave you plenty of time for the questions and answers as they get developed. So starting really the two slides I start with in this is the dual functionality of FTIR. When people ask us, well, what can you do? Essentially, there's two sides of the technology that really are helping people in the field. And that is, the first one is what we refer to as quantifying the known. Applications are not strictly limited, certainly, to occupational health and emergency response. They go into research and compliance monitoring, environmental quality control, just in case other people are out there with that. We can certainly talk in their particular applications. However, today, of course, we're going to concentrate mostly on the occupational health and safety emergency response aspect. But anyway, what we're really saying is that we can, with the technology, provide the ability to measure 50 gases simultaneously, so up to 50 can be measured, and they can be drawn from a bank of currently in the order of about 450 gases, can be brought into what we call an application library, and those libraries can then be changed depending if you're in maybe a chemical plant versus a university versus a semiconductor versus a refinery. Those list of gases, that your target gases, that we call them, will be different, and you will have those targeted to your specific applications. And then you'll go about quantifying those gases that you know are out there, the toxic gases. Then you can do that through this ability to quantify the known. So it gives us certainly a powerful capability. It's certainly, there's other capabilities, there's other technologies that this can happen, that can be done with. We can do organics and inorganics, but it's a powerful way of being able to provide in near real time the gases, target gases for occupational health and safety screening, etc. The second side of the technology, which adds another dimension of analytical power, is its ability to identify the unknown. So hence the hazmat emergency responder people of the world really enjoy this type of technology. But then coming back to the safety professionals who are being called on to solve problems and mystery smells and odors that are making their employees certainly with nausea and uncomfortable in the workplace, asking for a way to solve what's going on, what am I being exposed to, etc. So we have the ability through the technology we're about to show you to identify. We can draw on that 450 gas library, but we can also add to it the NIST EPA qualitative library, which is over 5,000 gases. So one can go into the workplace and certainly in 10 minutes or less can be identifying unknown gases. Then we're going to go through a few applications here, show you how that's actually applied. So it gives a very valuable, powerful tool for safety professionals to be able to solve air quality issues in the workplace. So that's the two that we're really going to look at. We're going to see how they're applied in a number of applications for this dual functionality of FTIR. In a broad sense, this one will will deep dive in that. But how is the technology being used out there? Certainly, measurements of VOCs in the workplace is a common. BTEX, yes. The methylene chloride, or DCM, is a very high-profile application currently with the new Tusker rules coming out. Formaldehyde, certainly with its very low PEL and toxicity there, is often being used. But waste anesthetic gases in healthcare, very sort of traditional application. It still goes, the measurement of the WAGs. Cold sterilants, ethylene oxide, you've got peracetic acid, hydrogen peroxide, as well as formaldehyde there. Emergency response, yes, these tools are very, very well received in that area, just because when they get their 911 call response, they have the ability to screen very quickly and identify these toxic gases at spill sites, at situations where it's not obvious what's going on. Other areas we get into with trace gases, nickel carbonyls, a very, very toxic gas used in certain industries, nickel plating industry, etc., refineries, in various situations. So it's a technology that can be very well received in there. Occupation health and research, certainly that side, it could take as a tool, can be used very strongly for the measurement of toxic gases related to various research projects associated with that. Sustainability, we show there the bottom left, the bottom center there, the Harvard in sustainability basically went about looking at air exchanges for risk assessment. What happens if we reduce the air throughput? That energy is money, is sustainability for climate change, etc., where you've just having your carbon footprint is high. How can we reduce that? So there's certainly studies being used where this tool is being able to quantify accurately the risk of various, the concentration and hence the risk associated with doing that, reducing air exchanges. Anyway, we're going to certainly get into those, but that's just kind of a host of possible applications. Everybody has a different workplace of different chemicals and different situations. Hopefully we can touch on some of that similarly for you. Starting initially, this presentation here was given at the American Industrial Hygiene 2020. Stephanie Callow and her colleagues, they looked at formaldehyde in a pathology lab there at Duke University. And near real-time analyzers giving you not only obviously a measurement, a direct measurement, but it's giving you a very powerful way to make changes so that you can assess the workplace. And that's essentially what they did here with the analyzer, took in to the pathology lab. They strategically placed it so that, and then they tracked the exposure levels that the workers were through their various steps, their stations of the pathology work that they were performing. And of course, from that, they can then go back and look at what levels of formaldehyde were in the air at the time, depending on the processes they were delivering. And sure enough, they found relatively high levels. And so after modifications of the workflow, they were able to go back and re-examine that and show, yeah, just with a few the new grossing station and a layout, changes in layout, etc., they could protect their workers, reduce the exposure level for the formaldehyde. But that again is how a tool can be applied from that research and then to put it into process so that they're improving the safety and of the workplace for these people. In the healthcare industry, as I said, this has been the use of those going back to Morans, the original Morans and Sapphires, etc., been performing waste anesthetic gas measurement for many, many years. This technology is well suited to measurement of waste anesthetic gases, which includes these days the desflurane, isoflurane, the sevoflurane, and nitrous oxide as well, and various studies and routine work is where they're going into the OR for the recovery, looking at waste leaks around the anesthetic gas machines, scavenger systems, etc., in the recovery rooms where the nurses are literally leaning over the patient and are susceptible to the exhaled breath, which will include levels of these waste anesthetic gases. So very important to keep a tight control on the levels in the operating room. It's a very important part of a healthcare system where a lot of the flow of the work is going through. So they need to have a tool they can rely on in the case of any smells, odors, things going wrong, etc., to be on top of it. Now, shows the badge. A badge, of course, is always a go-to for doing dosimeter studies, etc., where that around. And one hopes that after that happens and 2 weeks later when the results come to back that everything is low. But of course, when things go high, the badge is not going to help you identify the processes, when this happened, how this happened, that sort of thing. So the use of a real-time analyzer to be able to go in and inspect gives you that much more power, etc. So it's another value component. So for sort of cost saving, certainly always when we look at real-time instruments and instrumentation, there's a cost associated with it. So the question's asked, well, how can we have some sort of payback? How can the instrument really reduce our costs of that? And one area is this waste disposal, where unlabeled vessels, flasks, beakers, bottles, etc., are left out, and then the EHS department has to then decide how we're going to handle that. And so what is used, the FTIR is used to be able to identify what exactly is in those bottles. Is it simply a water solvent base that can be disposed of down the sink, or do we need to use hazmat disposal to dispose of it in a safe manner? And this is the ability, as illustrated on that right-hand side, for the safety technicians, etc., to be able to screen the solvents, the liquids that they have in their beakers, and then make sure that they can then identify the appropriate waste stream. And anything that's hazmat is costly, so it doesn't have to be done that way. Then they have a way of being able to reduce their costs associated with the hazmat disposal. So that was courtesy of the University of Wisconsin, Madison there, is one way that they were able to look at justifications of procurement and of usage of the equipment. This we were invited. Gasmet was invited in February. This was 2024, in a study that emanated from the county of San Diego. The measurement of lithium-ion batteries, certainly high profile these days. We know that well, proliferation of lithium-ion batteries globally, and then the implications in thermal runoff situations. These end up into being nasty fires, a lot of energy released in a short period of time. Well, for the county in San Diego there, with their sunshine and that, lot of EV bikes and automotive vehicles, etc. And so what had come from that was back in 2023, one of their workers was exposed in a EV fire, and they was off work, was exposed to hydrogen fluoride monitoring from the liberation of the EV. But when they tried to figure out what precautions, what they needed to be doing, they found there wasn't a lot of public information out there. So they put together a study where they really brought together, as we'll see momentarily, different vendors to look at different sides of what's happening in an EV event like this, where you have thermal runaway. What are the implications of the emissions from the toxic gases, etc. And so over 3 days, basically, they put together a program where they brought in batteries, brought in the ability to monitor it, put up with the sort of experimental conditions, and wanted to study more the releases from a EV fire. So here, very quickly, is what they got their hands on was the public works area, very kind of remote, so ideal to set themselves up. They built a cinder block, a little chamber or building, and then from that, inside that, we'll see in the next slide, is where the actual thermal runaway events of these batteries took place. As I said, it was approximately 20 different combinations of formulation sizes of batteries, casings of the batteries that they were in, etc. And as I said, Gasmet was invited in. We had I think there's RKI, measuring other components such as hydrogen and oxygen, etc. Here's the FTIR here, sitting outside. So the tubing inside the experimental chamber to the sample probe was run there. And for safety, then the system was back about 50, 60 feet away, using Wi-Fi or Bluetooth to talk to the analyzer, etc. So everything was set up in a safe mannerism, but with the idea of trying to really identify what was happening in these applications when the fires were taking place. So we'll use a little bit of audio video to show you what was happening. So there's the chamber on the left-hand side, being with the EV being put in, and that taking place. On the right-hand side, you see all these gases being measured simultaneously. Time lapses, we're talking 10 minutes there for that overall, but everything happens very quickly. Once the lithium-ion battery goes into that, and accordingly, we see these gases being liberated, high levels. The hydrogen fluoride indeed was measured at levels above the recommended exposure limit, etc. We provide our thanks to the County of San Diego, certainly for allowing us to participate in the data. Here, just pulling it apart, that's the 3 days worth of testing. So approximately every 30 minutes or so, we go through a new test on that. So you see the spikes at each of the 3 days, etc. there, and a list of some of the gases that were measured simultaneously. If we pull that apart into what the focus was the hydrogen fluoride, REL, recommended exposure limit, 3 ppm, the STEL at 6, and then the hydrogen cyanide, other gases we looked at simultaneously. So we plotted then with the data that was recorded. Here the acid gases first. In red is the hydrogen fluoride. 0 to 50 ppm is the y-axis. And again, we'll go across these various events, the thermal runaway events. And we see indeed, yes, it was 6 ppm is the red line for the STEL. We see that in a number of occasions, the HF went way above that in through the event, etc. Hydrogen cyanide was also plotted, 50 ppm, and we see again several times that went very, very high. And the other gases we'll talk about there in a minute. But we also saw in their formulations in some of the battery situations that there was no problem. Things were very safe, but in other times, due to the formulations being used by these EV batteries, there was very hazardous conditions happening simultaneously. Very quickly, CO, hydrogen cyanide. This time we're plotting CO to 1,000 ppm. So yes, in this incomplete combustion that happens very quickly, a lot of CO is liberated. The hydrogen cyanide, etc., is still quite high there. And formaldehyde, benzene were also plotted. And so a very toxic soup essentially is what is being shown there. But just to put this one kind of, so in your workplace, I'm sure you've got procedures to handle EV batteries and for lithium-ion batteries, etc. But just to kind of translate that real time, we certainly have, and I know it was one particular company that has a system, but it was carbon disulfide, and it was their process. So they could use the system to make decisions of when to allow workers to take off their to remove their PPE, so that they knew they could track all along the level of in this case that solvent carbon disulfide, and then could say, hey, now we're safe. And that, so any of these situations, when you have this near real-time information, you can make very accurate, and really for your risk manager can really make assess of the workplace very well. The next slide just we'll look at is the selectivity or specificity and sensitivity, the importance of those when you're reviewing real-time information or real-time gas analyzers. They should be very, very important in your, let's call it the due diligence of examining that. So we're going to use this example of how FTIR handles this selectivity or the specificity, and we're going to use the methylene chloride or dichloromethane as an example. So initially, just to say thank you to the University of Washington on the left side for the photos we're using there. I want to very importantly say the information or the data I'm about to show you is not from the University of Washington. It is real data, but not from them, just to differentiate that, and we'll see here in a moment. So let's play this short little video. So methylene chloride application, we've got methylene chloride and we've got ambient air gases. We'll talk a little bit more about that. We've set that up, and now we're going to review the data. So these are the spectra that were sent to us because there was some unexplained information in their mind. And we're reanalyzing. What we're plotting here is within FTIR, there's a residual value that's telling you the success of the analysis. Red is telling us it's an unsuccessful analysis. And so there's interference. There's other gases in the application that we need to take care of. So once that's happened, we basically have the ability to identify the unknown. So the software, after we click the identify, is taking the measurement and going through the database. And here it's found that also in this sample, there was ethyl acetate and there was hexane. So once that was added, we now have a green residual, so a successful analysis, and we can go back now and we can reanalyze. And so the data is being reanalyzed now with those additional two gases. The residual alarms have gone away, and we now have an accurate reading for the methylene chloride. So it's very powerful. So every time a gas measurement is made, we're actually stating a level of confidence, which is whether the analysis is successful or not. And that's very important to have this accurate determination of that. So if you were to use a PID or another detecting type of device like that, you would have false positives that would be happening to you. And this is the power of the FTIR to tell you not only the concentration, but to make that statement of accuracy associated with it. So that's very quickly just illustrating how that's coming together. This one was then another case study in the semiconductor world, and safety personnel, as we were saying, they were responding to alarms from an existing gas detection system. It was paper tape based. They were getting called out continuously, and there was no gas leak that they could verify. The system was showing a response, but they could not verify that in fact was correct at all. So essentially, you had this false alarming situation, which was causing time consuming and costly delays in the production area. So the FTIR was brought in to look at what was going on. So here, just sort of pulling things back apart very sort of quickly a little bit at the level of understanding the technology. We deal with, here's a spectrum. So we're measuring the infrared spectrum of a gas absorption versus the frequency in a clean sample. We've got water vapor and CO2, and we're displaying that. Here is values 400 ppm, etc. water. And we're also saying that in this, through what's called a residual spectrum, there is nothing left over. It's a clean line, etc. So that is the normal clean air. And most importantly, the software is saying everything is okay, that is clean. If we take this sample that was from the actual semiconductor from the fab in the vicinity of the odor that was being reported, this same spectrum now has your water and your CO2, but it has other responses, other unknowns that were in the air. And the residual shows you no longer a flat line. That residual then comes up in the software as a red residual, and then it says, hey, there's an alarm. So it's an unsuccessful analysis. So what they're saying is there's something else in the air. So how do we go about that? This is just a different display of the software, but we'll just play it quickly. So here's our sample on the right-hand side. We're going through this identification step, which can be going through the 450 gases in the quantification library and the 5,000 gases in the NIST EPA library. But it's making a match. It's trying to match this response, and each gas has its own unique signature, and it's going through that process now. So it's come up with 1-methoxy, 2-propyl acetate, butyl, acrylate, etc. So we're adding those to the application library. So we've got our ambient air gases, and we've taken on the right-hand side what we've measured, and we've reduced it down very significantly. There seems like there's still a little bit left over at the end of all this, but we've certainly been able to, with a 95% confidence level in the 80s, high 80s, identify these main components, okay? So what does that mean? Now, for the people out there, hopefully it meant more than a chemist like myself. Lots of nice chemicals, but I didn't particularly know what 1-methoxy 2-propyl acetate was. So we turned to Google, and I feel really old because these days it's all about AI, but we turned to Google in this particular case and say, all right, well, tell me what that chemical means in the semiconductor industry. And sure enough, it comes up and tells us propylene glycol is its another name, and it's used, in the semiconductor industry as in this particular processing step. So it was able to give the information. Of course, those professionals working in the fab in that semiconductor plant knew exactly what they were dealing with, and this was in fact a solvent that was causing the problems, causing the false alarms with the paper taped alarming system, and we're able to then get that resolved within their in their process to stop those future alarms. So it's how the technology is applied for both being able to identify the unknown specifically on that. Very quickly on this one, FTIR itself, then the infrared spectroscopy has been around for many, many years, 1800s. All asymmetric molecules absorb light with a unique fingerprint. So that's what that's about. In a specific area, there's the water there, water bending and vibrating. And from that, from Beer and Beer Lambert said, if you measure the y-axis of absorption, two constants, the absorptivity and the path length, you'll get the concentration. So quite simple, not particularly new. And there's only about 14 gases in the world that cannot be measured, subject to volatility for the others, but these diatomic and monatomic gases are not they have no infrared activity. So that means many thousands of gases can be measured with the technology. The developer was from Illinois, Dr. Mickelson, a physicist that was basically researching how to calibrate the speed of light. He is the forefather of interferometers, so this is his original concept. And what it was is the light is focused and put through a beam splitter, and basically it's split 50% through 50%, recombines through a moving mirror and causes an interference pattern. What's the big deal about all that? Well, the frequencies of light that you started with are all here, but they're encoded. And what happens next is it's then mathematics. The gentleman Jean Fourier says we can take this frequency versus time and transpose it to frequency versus intensity. So you get all the infrared light simultaneously. And then you go cherry picking. You say, hey, where's this molecule absorbs here? What's its response? What's its concentration, etc. So there's two phases. There's this physical measurement happens 10 times a second, and then mathematics takes over and transforms this into the spectrum. The big caveat of the technology is this component, and it's a laser. It's a helium neon laser, which very critically maps the movement of a mirror. And that means we have internal calibration. So we don't need to recalibrate for the gases that are measured. So once it's a one and done on those, but what we do to counteract for the transmission of light, which is effectively old age, is to do a daily zero. We take a gas, and typically your gas is nitrogen. Occasionally people will use argon or helium, but nitrogen's normally what we use, and zero the instrument at the start, and that just corrects for that. So in an FTIR, it's simple enough in its design. You've simply got your electronics, your normal circuit boards and power supplies, etc. This is the interferometer that's making this movement of the mirror. It's vibration insensitive. It's taken its 5th generation now for Gasmet. It's certainly part of very much of the technology that we can now put it on your back and walk around with it. There's a laser, etc. So that's nothing there that a user needs to worry about. That just happens, just goes on and does its thing. The gas sample is coming through. There's a pump, an internal pump pumping it through and out into this gas cell. And this gas cell has two highly polished mirrors that are protected from any corrosive gases, etc. And that passes in and out of the, but it essentially creates a path length, and we'll talk about that in a moment. But if we keep this gas cell dry and clean, we have a very low maintenance instrument. So all that's happening, I'll show you, is the gases coming in and out of this gas cell. Another aspect that we talked about before was the importance of sensitivity. And so it really differentiates a gas analyzer from a gas detector. So in the Beer's law, the B component is path length. So in an instrument like this, we're using a 5-meter path length to reflect it back and forth. All wonderful science, but what does it mean to the user, to you, and is the ability to detect gases at sub-ppm and ppb level. Mother Nature sets the absorptivity constant, which means its ability to absorb light. And so in brackets next to these gases, you see the detection, the theoretical detection for these gases. So a benzene's 50 parts per billion, a boron trichloride's 5 parts per billion, etc. So they all have, but we're talking about the sub-ppm, ppb, depending on the gas, etc. as well. The waste anesthetic gases, the sevoflurane, they're at 2 ppb, etc. So it's very important when you're looking at the final product that you know that you've got the ability. So, for instance, in that lithium-ion battery, we have 3 ppm as the recommended exposure limit. So here we are at 0.08, so well below it. For the methylene chloride or dichloromethane, 2 ppm is the recommended exposure limit there. And so here we have detectability down to 0.03, important considerations in the usage of the equipment, that you need to be much lower than the exposure limits, etc. How do we operate? So very quickly, operating, this is the model GT5000 Terra. So the layout, as we've sort of shown before, there is the gas cell behind this, but the sample is being pulled in by an internal pump through that gas cell, and what goes in goes out. So sample here with the pump, sample goes out this port, and then when we apply the zero gas here, it is going through the zero port here. The instrument has no display on it, so it talks, so it's applied to this ruggedized, Windows ruggedized tablet, and it can communicate to the tablet in a number of ways. You can choose a cable, short tethered cable, or you can go to Bluetooth or Wi-Fi. It has its own Wi-Fi IP address, so you don't have to be connected to a Wi-Fi for short distances, but you can remove these two and be blocks away, if not counties away, if you wish to, or have them on 2 different Wi-Fis. So it gives you plenty of flexibility. Anyway, so basically from startup, you've got AC power, you've got the battery pack as an option, about 3 hours. Get it warmed up, approximately 5-15 minutes. It really is thermal stability, and that's the difference of where things are stored as to where it's going to be operated. So it can be quite short time frame when they're in the same. And then basically do a background or a zero calibration. Is once it's stabilized, you're connecting a nitrogen gas, so big cylinder, little cylinder, whatever you're in the field or wherever you're at, this will connect into this. You'll be pushing a background button, and roughly 4 minutes, 3 to 4 minutes later, you're going to have your zero. It's a quality control check. You all being well, you'll move through to the next step. No span gases required. You can get straight into your monitoring from that. We show here then in a little bit more detail. So the software, the interface is called Calibration software. And so this lady here on the tablet is looking at the software, which is going to set up the operation. She wants to run the pump, etc., wants to do a zero or a background, wants to do any other checks. She can do it right through these large icons here on that. We have an application library. So here there's a list of gases. This can be up to 50. Here we're just showing 25 gases being measured simultaneously. The water and the CO2 always will be in the application since they're always in the air. We can have a trend. So this will give updated readings. How often? We can have 5 seconds, 20, 60. We can go a little bit longer. But what happens is that the optimum is at 60 seconds. That will give us the optimum of signal noise or lower detection at that level. But for leak detection, we can go faster survey work. We can get data every 5 seconds or every 20 seconds. The readings can be updated, etc. The software will then allow us to trend. You'll see the last reading, but what was it 10 minutes ago or 15 minutes ago? You can plot concentration of gas versus time and the spectrum then. But overriding that, you've got the OK. You've got 2 alarms. You've got your classical concentration alarm. So you can go in as a user and decide what concentration, and you can have a low and a high as to warn you when things are coming to a level increasing in concentration. That's number 1. And as I've alerted to before, and that's what we've showed quite heavily with the specificity, you're getting a residual alarm, which is telling you this unsuccessful, which means unknowns. There's something else in the air. So even though you've got 25 gases, there's potentially a 26th or 27th gas in the air at the time of measuring, which just makes sure that you're not missing anything. The data itself is then saved as a text file, which can then be imported directly into Excel. So again, you can have your date and time and do more deep review of the measurement data, etc., graphing and saving, reporting, etc. On that. So it just gives you a quick overview. But what the idea is here is to give you a simple to use a simple interface, so the user can go out and quickly be recording their measurements or identifying unknowns. FTIR and optical in general, if we put it in the optical category, is inherently a low cost of ownership. You don't have carrier gases and calibration gases, things that can be costly in the operation or the ownership of an instrument. Here, we're talking about the zero gas, so it can be supplied locally from your supplier there, Lessman Instruments or your supplier of preference, and we're looking at just a UHP grade, very low consumption. It's used per usage, about 10 liters, etc. And the only other consideration is the particulate filter. The only conditioning done is we pull the gas through, and that is to keep out the higher level of dust, etc. So a 2-micron Teflon filter sits in here, and this should be checked periodically. See, there's no buildup, no discoloration, etc. With that. So it gives for very low maintenance, etc. And no need to send it back because you have internal calibration happening. You'll be alerted certainly through the quality control process if there's a need for attendance. But if we look after that cell, keep it dry and clean, that can be extended for many, many years. Publications. So to start with, the FTIR is a recognized method, test method. NIOSH test method 3800 is for the measurement by FTIR of organic and inorganic gases. EPA and the ASTM have comparable test methods as well. Certainly over the years, many publications using the technology in industrial hygiene, emergency response, military applications, etc. We have a unclassified report from the US military. That's our single largest user, over 80 analyzers used by the military. And they looked at very extensively to say, hey, let's look at what the claims are here. Let's bring it into our research lab. Let's challenge it with a number of ticks and challenge and see what we think. Well, this is one paragraph from a 40-page report, an unclassified, that we're happy to share with you. And it looks at the sensitivity and the selectivity. And basically it said that, it basically it found it to be very sensitive and very selective for what it was measuring here, 1 ppm levels, etc. So down at very low levels. So that's an assessment, was a three-month study, etc. The American Industrial Hygiene Association has certainly released a booklet that covers the various technologies, the FTIR's Chapter 8. And if you want to really get in a deep dive of the technology, etc., it's all there for you in a technical level. We encourage you to look at that. Here, very quickly, rounding things off in terms of pricing, we certainly have divided it, recognize on the left-hand side that some people don't need all the analytical power. They just have a routine application up to 25 gases. So we call that under the basic level or the quantify the known level. And from that, the price to really to step in with everything, the tablet, the instruments, in the order of about 60,000. And those who need the full power, the package, which includes up to 450 gases, the ability to use those, and the NIST EPA library, adds approximately another 20,000 to it. Those perhaps from the federal, although unfortunately probably right now there's not too many federal people on due to the situation, a sad situation, but we have a GSA schedule whereby there's some discounts for them on that schedule as well. Last slide, just to round it up for you in this FTIR gas measurement technology, what's being offered here. The ability to respond to up to 450 gases and measure up to 50 of those simultaneously. And this is all available in approximately 10 minutes or less from arriving to site, etc., getting it warmed up, getting it zeroed, and away you go. This ability, as we've shown in several of our applications, this identifying unknowns where you're walking into a smell or an odor situation where you as a safety professional are being kind of brought in to solve and resolve situations in the workplace associated with gas leaks and smells. You can do that with the identification tool that's inherent in the Calcmet software, and do that within that 10, 15 minutes. You'll have answers coming at you. Ease of use, it's a work in progress. So now we talk a bit of history. Gasmet released their first model in 1995. The first portables came out in 2008. The Minneapolis at the American Industrial Hygiene was generation number one. This is generation number three, the model GT5000, and the software has evolved as well. We're now at the 14th edition. Embracing the feedback and the questions and that as to how we can improve it. But we have put a lot of emphasis on this ease of use for ability for people to be able to quickly pick up the instrument and be able to be productive with its use in the field. Validation, the FTIR is providing a tamper-proof spectrum with every reading it makes that can be re-examined by yourselves, by professionals, by people at Gasmet, etc., that can help you when you need further assistance on that. We talk about this low cost of ownership. Sure, there's a capital cost, a significant capital cost. However, the good side of the thing is that it's not going to cost you too much to operate into the future. Certainly expected 10 to 20 years of operation from an instrument like this. And the last one to round it off is this sidestepping redundancy. If we go back to 2008, that library we talk about now of 450 was 170. Each year, Gasmet adds gases to that library available to our existing customers, and that will continue so that as new gases come out into the field, freons or whatever, you'll be able to add those to the instrument or to the software in particular to expand its capabilities to the future. So with that said, thank you very much for your time. We'd be now very happy to assist you with any questions or feedback that you may have.
Thanks, Jim. Sorry, I had to click off my audio button or click on it. Few questions just to kick us off. And that is, so what happens if there's only a trace amount of a chemical, but it's not in the library?
Yeah, good question. So the spectrum tells us response. So if we see there, yep, we see, and we can go in very, very low and we can see there's something there. We put it through the identification, which would be, again, the 450 gases from the quantification library of Gasmet and the 5000. And it will tell us by fit. So it can tell us nothing, or it can look at some of the areas and make some suggestions of what chemical group it can be from. Now, you really, for the untrained, and certainly, in the emergency response, they'll be looking at, a high quality hit, and from that they can assess. But if it's not in the library, then you're not going to get a high quality fit. It's be simple as that. It's got to match. So I didn't sort of go over in big detail, but every gas has a unique fingerprint like human, and that's what it's fitting. And gases can have similarities, which just means that, all right, well, I see a similarity, so I'll give it a 60% hit. If it's the real thing, I'll give it a high 90% hit. So you can interpret, I think in general here, the summary is you interpret by the results the identification tool is providing.
Awesome. And thank you. Can you tell us a little bit about what kind of maintenance this needs and how frequently?
Yes, very, very good. And that's really related to the gas cell. I mean, let's take a step back here. We've always advocated that treat it, treat the instrument like you would your laptop, for instance. Drop it on the floor and let's hope it comes back. But it's not designed, for that. It's designed to take shock, sure, pop it down, hit against a wall or something, sure. But so as long as it's treated with respect, it's an analytical piece of equipment. There is no sensor to replace. The gas never touches a detector that doesn't exist. It's just going through the gas cell. So as long as we keep that gas cell dry and clean, so we're keeping the clean part from the filters, the 2-micron filters are going to do that. Non-condensing sample is a specification that's provided. So You should not have hot, moist gas going through. You shouldn't be putting in a steam sterilizer, trying to figure out what's in there, etc. You want to reduce that, bring that into a Tetlar bag and subsample those sorts of things. So as long as it's ambient air, then the rest is very periodically. You're going to change the particulate filter, and we suggest there you can inspect it every couple of months. But once you start to see discoloration, then sure to change that. But it has a low cost of ownership, as in consumables. Looked after correctly, we don't expect the instrument to be returned over for 5 years. If you can keep that cell clean and dry, and you will see that every time you're doing a background or a zero, you'll see the quality of the actual optical health of the optical system. So that is the main one. So again, you can't poison it. There's no way a gas, whether it's hydrogen fluoride, ammonia, they're quite corrosive gases. We do really stress the importance when you finish with the instrument, when you've done your testing, is to bring it back into a clean area and let the ambient air run through it 3-5 minutes. So when you stop it, put it back in the case, etc., you have a very clean system that no gases are going to be in there doing any harm while it's sitting there.
Thank you. So what about calibration?
Gasmet is calibrated. It's all on first principles. Those call them the 450 gases. So we have purchased from a reputable supplier, chemical supplier, the Mercks of the world, etc. The chemical in gas phase or in liquid, depending on the nature of the chemical, and done calibration curves across a particular measurement range. So we didn't deal in deep detail, but we come across, let's just call it hexane or ethylene oxide or methylene chloride. But Gasmet provides a measurement range 0 to 50, 0 to 100. It normally is in conjunction with its toxicity. Would be the most toxic gases, we might have a 0 to 20 or a 0 to 50. The non-toxics maybe 100 or 200 ppm. Plus or minus 2%. So a calibration curve is performed in the factory and quality controlled, etc. So that's the deliverable with the instrument in the Cockburn software. Under the technology, as we referred to before, because of that internal laser, you never need to recalibrate any of those gases because you are tracing them every time with a laser for the reproducibility. They can't move, the frequencies they absorb can't move. That's a physical constant on that. So there is no need for calibrations. You yourself can, it's not proprietary. Should you wish to add a chemical, and you can do it, you prepare calibration curves, etc., you can calibrate for an extra gas, etc. And so that's quite possible. All we're asking is that zero. The zero just it locks the 0 point or the 100% transmission point through the instrument. That's the most important part, is to do a zero at the start of it. That gives you the quality control aspect, but no calibrations required.
Awesome. I'm looking through, and it looks like most of any other questions you have addressed in your last slides, with the exception of one, just saying if you can just repeat when you feel it's appropriate to go from the CalcMet Easy to the CalcMet Expert and get that additional library. When would that be appropriate for someone to be considering?
Mm-hmm. And so on that left-hand side, this is the pricing and how it's done, is that we have customers that have defined applications, and as long as it's less than 25 gases, that's part of the deal, is that we will provide an application library. You get the hardware, you get the tablet, the wand, and that you get everything you need, a battery, etc. And you get one application library of up to 25 gases. Those 25, which will include the 5 ambients, water vapor, CO2, methane, nitrous oxide, and CO, are always in our basic application library, and they have the ability to select up to 20 other gases from that. So that's their defined library. The software in that basic site does not allow them to change it. So that would be step one in the future, if that was that. But it's mostly associated with unknowns and things like that. So if they want to have flexibility and change the libraries, they really have the need to expert. And if they want to do unknowns, as in they are in situations where they're responding to odors and smells, to situations where they may not know the full list of chemicals, those people, and generally within the hazmat world, that defines it straight off. The hazmat situation defines that they don't know what the next call is all about, so they will need it. But respectfully, we know some people have a straightforward. A hospital would be a situation where in a day-to-day situation, they probably know the chemicals that they're dealing with. And the nice thing is there's an easy transfer procedure where they can upgrade in the future. So if they purchase it at the basic level, in the next year, next budget, or budgets to follow, they can upgrade the software to the expert. So that's not a problem.
Thank you. Beyond that, you've done such a good job. There aren't, I don't have any more questions. I would like just one thing that I'll bring up also, just because it wasn't discussed earlier, is just that this is portable and there's a backpack that comes with it. So it's something that can be carried around to different areas with ease. And if there are no other questions, I just want to thank Jim for, as always, you are an excellent source of information, and we really appreciate when you come. If anybody on the webinar has any specific questions that either weren't addressed or come up later, please, my information, my email is on the screen there. My phone number, my direct phone number is 630-757-1755, or rickd@lessman.com. Also, if there's information about other technologies that we support, we have webinars that we post all the time on many different industrial hygiene and process instrumentation, and just let us know and we'd be happy to bring in like Gasmet, our other sources. So please don't hesitate. And all of our webinars will be posted on our website or at lessman.com or on our YouTube channel, Lessman Instrument Company. So if you're ever looking for this or any other webinar, you can go there and go through the library and find some useful information. Beyond that, I'm still looking, being that there's no additional questions. Jim, I thank you very much for your time.
Thank you. And just to say, it's a team effort. Steve Oakes is with us, and Gasmet's, we have much in the way of support, answer those questions, etc. So I appreciate that. But it's not just Jim Cornish; it's a whole team of experts behind us here.
Absolutely. And Steve and I are always happy to come on a Teams call with anybody if you have a specific interest, application, or you would like to present a presentation to your team. Okay, so with that, thank you again, Jim, Steve, and we look forward to the next webinar where we get to see you all.
Bye for now.